All right, so let's look at another problem where we're determining intervals of increasing, decreasing, concave up and concave down, and then justifying our relative maxima and minima using the first derivative test and then the second derivative test. All right. So bearing that in mind, we need to find both the first derivative and the second derivative of our function. So our first derivative is 3x squared minus 12x. And our second derivative is going to be 6x minus 12. So now we set each of these equal to 0 to get our critical points, which would be the first derivative equal to 0, and our potential inflection points, which would be our second derivative equal to 0. We pull out our greatest common factor, and then this expression is 0 if the first piece is 0 and if the second factor is 0. So we're going to set each of those equal to 0. So I have 3x equals 0, which occurs when x equals 0, and x minus 4 equals 0, which occurs when x equals 4. Now we do that number line business with the first derivative. We're going to check values on either side of our critical points. Right, so remember our derivative equals 0 at these points, and we're trying to figure out increasing, decreasing. So we're going to be looking at our derivative on each side. So I could use -1. And that would be 3 times 1 minus 12 times -1. So 3 plus 12, 15. So we're positive here. So that would be increasing because we're positive, our first derivative. And then pick a number between 0 and 4. So I'll choose 1. We got 3 minus 12 times 1. Oops. And that's going to be -9. So this is decreasing. And our first derivative is less than 0. And then lastly, we got to pick a value bigger. So I'll do 5. And this one would be 5 squared 25 times 375. Minus 5 times 12, 60. Positive 15, so we're increasing. And that means our first derivative is greater than 0. All right, so we'll write that in interval notation in just a moment. Let's go ahead and do our second derivative for concavity first. So when you solve this guy, you're going to get 6x equals positive 12, divide both sides by 6, x equals 2. At that point, our second derivative equals 0. So, whoops, that should say 0. We have to test a value on either side. So I'll do 1 on the left. We get a negative. So that's going to be concave down. I should have left more room for myself. And that's because our second derivative is less than 0. And then we'll pick a value on the other side. Look at me not leaving enough room for myself again. It's positive, so concave up. And that's going to be because our second derivative is greater than 0. Notice we change from concave down to concave up. So x equals 2 is an inflection point because we change concavity. So because our f derivative goes from negative to positive. All right, now we're ready to write our intervals. So I've got increasing, decreasing, concave up, and concave down. So looking at our first derivative line over there, we have everything to the left of 0 is increasing, because it's got a positive first derivative, so negative infinity to 0. And then we've got everything to the right of 4. And between 0 and 4, we've got decreasing, because our first derivative is negative. Concave down, we've got everything to the left of 2, so negative infinity to 2. Concave up, we've got 2 to the right, so 2 to infinity. All right, so the first derivative test, we're looking at the values of the first derivative. So we're going to be looking at the information we have on the left side. So x equals 0 is going to be a relative max. And that's because our first derivative, let's just write f prime, x changes from positive to negative. So if you want to think about it visually, you could do, why can't I write right now? Negative. So if we're thinking about it visually, we're increasing on the right of x equals 0, and then we're going down, decreasing on the other side. So that's why it's a relative max. At x equals 4, we've got a relative min. And that's because our first derivative changes from negative to positive. If you're thinking about that, a negative first derivative means decreasing, right? And then we switch to increasing, a positive first derivative, which makes it a relative min. The second derivative test has us looking at the second derivative at our critical points. So remember, our critical points are where the first derivative equals 0. So our critical points are x equals 0 and x equals 4. So now we look at the second derivative at those points. So our second derivative was 6x minus 12. So at 0, we've got 6 times 0 minus 12, or negative 12. First derivative, that should be a 0. At 0 is negative, right? And when it's negative, that means it's concave down. So if we imagine concave down, we've got a relative a relative max. Yikes. All right. And then same thing at 4. 24 minus 12, 12. So our second derivative at 4 is greater than 0 or positive. So we're concave up, which gives us a relative min. All right, so you would say at x equals 0, there is a relative max by the second derivative test, because the second derivative of 0 is negative. All right. And then the opposite would be what you write for the second one. So at x equals 4, there's a relative min. By the second derivative test, because f double prime of 4 is greater than 0. And that's all, folks.